talked about is we went one step further and we say what is in the photo based on what our system thinks. And we can even take it even more, which is not only say what is in it, but the person can touch the smartphone and know where is it, how big is it, and so on and so forth in the next few versions. So this version specifically uses the image classification, and let me play it.
Wonder what it's like to use Facebook if you are not able to see? Turn on your sound to experience it. Screen readers, like this one, read aloud what's on the screen, making Facebook accessible to the millions of people worldwide who can't see. And now Facebook's new technology can tell them what's in a photo. Facebook, search. What's on your mind? Xiaomi Wu, March 6 at 10:14 p.m. With my college buddies in my favorite place. Ready for a great weekend. Photo, image may contain.
Honestly, and this talk should convince you that we are moving away from it, where we annotated each and every image with respect to the task that we were training the system for. We can move away to weakly supervised. One of the beautiful things about deep learning is it's very noise resilient. So if you have a lot of noise in your labels, deep learning can still explore the signal and ignore the noise. There are certain gotchas there, but I can make that statement and go into the details. So that's the weakly supervised learning. So in weakly supervised learning, for each of the image, you have certain information, but you don't know with certainty whether that is correct or not. So it's a probabilistic label. In a semi-supervised setting, you have a lot of data of which only some part of the data is labeled with full accuracy, but rest of it is not labeled. But as you can imagine, you can see similarity or clustering and you still use that information or the unlabeled data to build a better model. So that's semi-supervised. There are many versions of semi-supervised. One example is that. The other example is we are trying to do detection, which is a bounding box of a thing, but you only have labels that are image level. You can call it weakly supervised, semi-supervised, but you don't have the full information. And then self-supervised. Self-supervised is the holy grail where you just have data and you're somehow learning representations that are super useful for various tasks. As you go from left to right, you can actually increase the amount of data that you can use to train the model because you don't have as much limitation on annotation budget. In the fully supervised, you will probably have to use thousands of annotators for hundreds of days, hundreds of hours, I don't know, millions of dollars, depending on which company you are or what task you're tackling. In weakly supervised, you can basically get rid of some of that bottlenecks, semi-supervised even more, and self-supervised, you can get rid of humans completely in training the systems, not in any other sense. So I'm going to talk a little bit about how we took that bottleneck as an opportunity and pushed the state of the art. And specifically, I want to focus on weakly supervised. So this is work that came more than a year ago now, and still I believe is state of the art on ImageNet benchmark, which is the image classification benchmark that a lot of people benchmark their models on. So one of the intuitions that we had is people upload a lot of images to Instagram. Instagram is another product that Facebook has. And for every photo that people share, some of them don't upload any hashtags. Some of them upload a gazillion hashtags. And some of those hashtags have meaningful information, but a lot of them might not have meaningful information. So one of the intuitions that we had was, can we leverage this information? And is this weakly supervised setting allowing us to train a model? Our best bet was to train a model that is as good as a fully supervised model. But turns out, because of the scale, we can actually do better than a fully supervised model, even in the noisy setting. How did we do it? So when you're training at a billion scale, it's not just the number of GPUs or how you train the system in a distributed way, it's also how you're going to leverage this information. So it has a bunch of challenges. One of the obvious challenge is you can get a bunch of these hashtags. In a fully supervised setting, the human will help you saying, there is a cat, there is a dog, and they're on the wooden floor. Great, I have full information, I'm going to use it, train a model, that's fantastic. But in the real world setting, what happens is, I'm a cat person, so I'll hashtag a cat. I don't care about the dog. Or I'm a dog person, I'll hashtag a dog. I don't care about the cat. So on and so forth. So you can have labels that are correct. You can have labels, I love my cat, so I do want to put hashtag love. But that's not useful information to train a model. So it's noisy in the sense of training a model, not in the sense of somebody sharing a photo on Instagram. You will have missing labels. Now, if I'm sharing a photo, I'm not going to enumerate everything that is in a photo. I'm just going to enumerate what I care about, right? turns out, when you do this at scale, each one of us cares about certain different things. So it does work out that over time, you actually start getting the signal that one person might not give, but the other person gave. So if a similar photo is uploaded by another person, they probably would care about some other parts of the photo. So you will have missing labels, and finally, you will also have incorrect labels. We are humans, we make mistakes. So we think we have Husky, but we have another brand. So the idea is, how do you take all of these challenges and convert them to opportunities? This is one of the core problems, and this particular work we were trying to tackle that. So what we did is we took billions of such images, and each of the image can have any number of hashtags. We picked the first few hashtags. I don't remember the exact number. I think it's between 5 and 7 or 10. And many of those hashtags, now you can imagine those hashtags are, some of them are visual, some of them are not. There is noise, there is missing labels, there is incorrect labels. How do you deal with it? The first thing we did is prune the label space. We took the hashtags. Can you believe how many hashtags you can get, unique hashtags, if I took a billion images? Does the room want to venture a guess? How many unique hashtags will there be if you were to work with 1 billion images?
10,000.
How much? 10?
10,000.
10,000? 10 billion? 10 million. Keep going. No, okay, we can come back. It's actually around 10 billion. It's insane. So the crazy number of hashtags that people use and how unique they are, it's a long tail of unique hashtags. Many of them are super representative and many of them are not. So what we did is we took that crazy number of hashtags, we looked at the histogram or frequency of if it's used once, which is Indaba enjoying CV Summit 2019, I will be the only one doing it. So you take those hashtags with enough frequency and you intersect it with the wordnet. Wordnet is actually a hierarchy of words, and you take the subtrees of the wordnet, which is around 17,000, and we just pruned everything else. So we trained a model on the 17,000 label space. And I don't want to go into the details because many of these things are in the paper and you can always follow up, but the core essence of this work is we trained on billions of unique images. This is important, billions, not millions. If you train on millions, you're not going to beat fully supervised. You have to train on billions to beat fully supervised. We train on humongous models. So because we have data in the billion scale, we were able to train models that have much larger capacity, 10 times more capacity than you can imagine, like a ResNet 50 or a ResNet 18. So we are talking about ResNets 100 and 1,000 and so on and so forth. We trained on thousands of labels. So in ImageNet, there are 1,000 labels. In our case, we went between 17,000 to 20,000. And we also trained on models that are in the order of 100,000 label space. And finally, to do all of this, we have to do it in a distributed training manner. I'm going to put a plug for one other work, which I think is extremely important work. If you are doing large-scale distributed training, you should definitely check out this work. It has all the core essence of how you would train a large-scale distributed model on what parameters to set, what are the learning rates, how do you change the learning rates, and so on. Using this work, we were able to train an ImageNet in 1 hour. So the models that I was talking about, the billion scale and humongous models, they took us 3 weeks to train using around 400 GPUs. The more important bit here is the 85.1% accuracy. This, I believe, is still the best on ImageNet benchmark, and this was a significant improvement because everybody was improving on ImageNet benchmark with 0.1, 0.2%, and we got a 2% jump because of weakly supervised learning at this scale. One of the themes that you will notice is whenever we have a technology impact, I'm never happy with that. That's a starting point for me. How do you take that and convert it to real world? How do you make sure that people actually leverage this change in technology or change what is a meaningful change for them? So previously, we would give certain outputs for these images, the description for visually impaired, for example. And we would miss a lot. It's like Taj Mahal is one of the many wonders in the world, and we might not have a class for it. But because there are so many people uploading photos of Taj Mahal or in front of Taj Mahal with the hashtag Taj Mahal, our system already knows it. And now we can do a much better job of describing something beyond food. It's like, what is it? It's a cupcake, and apple pie, and Taj Mahal, and so on and so forth. This gives a much finer understanding than what was previously possible. And as you can imagine, these networks learn representations that are not specific to the task, but more generic. So we took that representation and we trained it with a captioning system. And there, if you train the ImageNet model, which is a model trained on ImageNet, you take the feature and ask for that system to caption these 2 images, it will give you that. Whereas if you take our weakly supervised learning model, you will get those descriptions. much richer, more contextual, and they understand the semantics of the image more because they have seen billions of images with the right hashtags. Yes?
Do you make any attempt to quantify the value of a particular sample? So like if we can't get the Facebook scale data, do you have any strategies for actively choosing what the sample is?
This is a great question. So the question is, have we done any work on understanding, let's say, do we really need 3.5 billion images, or can we get the same representation with 30 million images? Stay tuned for the next CVPR, but answer is yes. Answer is yes, actually yes. So we found a way to train a model with 50 million images that gets 99 point whatever percent of that 85.1% accuracy. And the way, I can give you the information, the way we do it is purely based on similarity. So we think of similarity, image level similarity as the Q. So we have trained models with only 50 million images that actually get you the same level of accuracy. But how you select those 50 million images is the key, and that's what the paper is about. Yes?
By the, the hashtag is like Statue of Liberty. Like, how do you do that?
Oh, fantastic question. So I told only about, so all of these, the question that a person asked, that is not in the original paper, but this particular question, the answer is in the original paper. I didn't go into the details. So synsets, WordNet synsets is one particular aspect of the work. The other particular aspect of the work is doing pre-filtering on the hashtags where you remove special symbols, doing word-to-vec embedding and clustering them and removing duplicates and so on and so forth. So Statue of Liberty, for example, in many languages means many different things. So we try to cluster all of them and still use images. Images are more universal. Hashtags and language is not necessarily universal. There are many languages. So the paper talks about all the pre-filtering that we do, how we use WordNet synsets, and so on and so forth. Yeah.
Definitely most of the images.
Low quality and high quality. That blurry photo of my kid running is super high quality for me, but might be super bad quality for compression, or when you think about high def. So one of the nice things about working at 3.5 billion scale is you get a really good spectrum of high quality and low quality, where quality can be thought of in many ways, whether it's blurring, whether it's using a professional camera or a mobile phone. And actually, I've seen many photos of Taj Mahal where Taj Mahal is probably visible only 10%. Rest of it is a selfie. So you have a huge, and so that is that low quality, probably from a Taj Mahal training perspective, high quality probably for the person who took the selfie. So we do have a huge spectrum on quality, whether it's DSLRs or mobile phones or occlusions and various weather and so on and so forth.
Which is the case already. You just look at the most frequent hashtags and then you use a tree to broaden the rest of them. But definitely then you would end up with images with staging tool, for example, to improve the accuracy or the labeling. Or
you all should come work for Facebook. This is definitely one of the directions, which is you can actually let go of many, and it's okay at a billion scale. So I was also worried about it because you're at billion scale. So the assumption is if you're depending on that one important image, you're anyway failing in the way you're training this model. So we have not had an issue of certain images disappearing and the model not learning the right things. Okay, 100K hashtags, and there is a delta difference. It's not like a make or break from our observations. So the good news is all of these models are available, and you can use those representations for your apply. You can start off, instead of an ImageNet model, the weakly supervised learning model. And it's as simple in PyTorch. Hopefully some of you have used PyTorch. It's very, very simple. All you do is load the model, and there are certain names for it. We have a bunch of models that are available right now on GitHub, and you just evaluate given an image. And you will get, using the weakly supervised learning approach, that will still beat ImageNet. So use these representations wisely. With great power comes great responsibility. So I talked a lot before in my life. I know some of the problems that you're talking about. The generic answer is, if your input distribution is, while you're training, is similar to that are more blurry in terms of when you apply the model, you might want to change the distribution of your input images by doing data augmentation, where you blur the parts of the images in the same way. You might want to simulate car moving farther, car moving closer, some weather patterns or exposures and so on and so forth. So one of the generic techniques is you try and align your, with respect to this particular problem, I mean, license plate has certain dictionary to it. So you're not going to find arbitrary characters. There might be certain vocabulary that you're looking for. So even if some part is occluded, you can probably fill it in, and you can use a language model, you can figure it out in terms of you assume that it's characters and numbers and so on and so forth. So the specific answer is use the domain-specific knowledge to incorporate as part of the final evaluation of the model. So your model is not just taking an input image and producing an output, you're post-processing the output, you're pre-processing the input as best as possible, taking the assumptions of the system. So we talked about how the world is moving towards richer ways of Messenger, Oculus, which is VR and AR. Every single app, video is first almost. Everybody wants to experience as if they are there. How do you think about video? Do you process a frame every second and you're good? If you did that, you're going to miss a key moment. This is an example where that's a frame before a second and a frame after a second. And what did you miss, or what did the model miss? It actually missed that. That's bad, right? So, but then what do? Do you process every frame? In which case, it's going to be super expensive. So how are you going to take this data, and we know that there is going to be redundancy with certain spikes of information that are critical for the task that you're performing. How do you identify those spikes and focus on that? Pay attention to that. This is a long-standing problem, and there are a few ways we can tackle it. That's one of the problems in media. 2014, the model called C3D. So in many of the images, we use 2D convolutions because you have a 2D image. In case of video, you have temporal context, which is three-dimensional information, right? Over time, space and time. So we just adapted some of the best models. Actually, the lab that Daniela comes from, VGGNet, we adapted VGGNet to have 3D convolutions. And at that time, NVIDIA did not support 3D convolutions, so we had to do all of the... You're going to spend a good week doing it, and it's awesome. It's one of the best experiences that I've had. So what we did was trying to... the forward prop for a 3D convolution is super easy, but the backward prop is actually much, much harder. So we were at it, and what we noticed is, even though the model is significantly expensive, it actually gives you a significant bump in accuracy, because the model inherently is representing both space and time. And that's what we use C3D for. Over time, though, I always have the efficiency hat on. So you always need to keep switching between the accuracy and efficiency hats. So as we were thinking about efficiency, we started pushing these models. So we introduced Res3D, which is residual connections with 3D convolutions. And then we introduced Res 2 plus 1D. Jan had this extremely awesome intuition that you can factorize 3D convolutions plus 1D convolutions. And it's faster to train, uses less parameters, is more accurate. How much better can it be? So that was Res 2 plus 1D, but we didn't give up there, because what we did is channel separable networks. So we started separating and factorizing the channels itself. So all of this work, I have a slide on references. You can take a photo. You can go into the details of the evolution of these models. This is almost 5 years of work on building models for video understanding. And the size of the bubble is the compute that is needed, and the accuracy is the y-axis. So the good news is, even though the video is increasing, we are actually pushing out models that are becoming... One of the things is you have a lot of frames that come together. You have a bunch of audio that is coming together. You want to understand all of this information in the right way, with the right compute, with the right accuracy. So what we noticed is there are points of interest in a video, like the basketball, where you actually make the shot versus not making the shot. And we trained a model that only looks at the audio. So that model is super fast. It actually runs at 2 milliseconds and tells you, with more false positives, you should focus on this, don't focus on it, this is redundant, focus on this, don't focus on it, and so on. So it gives you the action of interest that you focus on, and it's reasonably resilient to noise, and so on and so forth. I remember the slide. That's actually my all sorts of funky stuff every day. So instead of getting 5 minutes of video, I want to go to the most important moment, which is, did it actually make it? And yes, it did. So instead of seeing 5 minutes of video, I want to be able to see those 3 seconds. How do, which is, we quickly scan through the whole video, all frames, with a cheap model, and identify. So this is a typical way of doing it in a spatiotemporal CNN, which is very expensive. So in the other way, you just look through it, you identify the key components, so you optimize in an end-to-end manner the selection, the training, and then the final task. You could do this in a weekly supervised way. Why should we apply weekly supervised only for images? You can do it for videos. And again,
what about in real time then? How would you do it? Or is it only on videos that you record and then you would be able to do it? How would you do it then in real time?
Good question, and the simple answer is none of these models make a requirement or have a requirement that I need to look at the history. Now, I actually think that's a bug. It's not a feature. We document it, a documented bug becomes a feature. So, so in this case, it's kind of a limitation of the system that it's feed forward. And depending on the size of the memory, if you're using an LSTM on top of the spatial temporal CNN, you probably have to accumulate few frames and do a batch processing. But in this case, it's actually, I believe, 10 frames a second, so you're talking about 0.3 seconds of latency. But we are working on models that are more long-form video. This is actually early work in Facebook AI research, and it's not clear to me on how we can change the predictions of the future based on the past, and whether there is actually any model that is going to look beyond even 30 seconds today in a good way.
There's like, I feel they call it fast compression or so for action recognition, optical flow. I really just hope that you can just touch on that in the video part, because it was very quick how you just brushed through it, but I would really, really like to hear from you with regards to that part.
Yeah, I'm happy to talk through it afterwards, but from the specific point on using optical flow. So if you look at how video is compressed today, you have MPEG-4 standards, you have H.264 and so on and so forth. And video is actually right now, most of the time stored in a compressed form. So one of the projects that we have, and I think we published in this CVPR itself, is how can we, instead of decompressing it, if you can imagine, decompressing video is as much compute as processing video with deep networks. So if we could somehow work in the compressed video domain on the final task, that would be amazing. So this is research work. It's not in production, or it's not fully working. But what we did is we took the compressed video, and in compressed video, you actually have optical flow vectors as part of compression, because that's what video compression techniques use to compress the frames, subsequent frames. So you have iframes and p-frames and so on and so forth. So we have models that actually work in compressed video domain that can do the same task of action recognition than in uncompressed. So that's one aspect of it. And the other aspect of it is what I was touching on, which is instead of processing all the frames, we select the frames using the SC sampler. That's one. Instead of using a 3D convolution network or a 2D network and as LSTM, we use channel separable networks, which are more optimal in my mind. And there is some work, I don't know if Natalia is going to touch on it, or slow fast networks, that is also from Facebook AI research. So there are few models that can do that. And finally, you can learn representations that are agnostic to the task, so that you process the video once, and then you use the same representation for many tasks. So I'm happy to go over at the end of it. We only have limited time, so I didn't go into the details.